This is the basic characteristics of soils. So the nature of soils. I'm just going to read it through this time. Um, the nature of soils. To the civil engineer, soil is an uncemented or weakly cemented accumulation of material particles formed by the weathering of rocks, the void space between the particles containing water and/or air. Weak cementation can be due to carbonites or oxides precipitated between the particles or due to the organic matter. If the products of weathering remains at their original location, they constitute residual soil. If the products are transported and deposited in a different location, they constitute a transported soil, the agents of transportation being gravity, wind, water, and glaciers. During transportation, the size and shape of particles can undergo change and the particles can be sorted into size ranges. Just a little note for me. I remember doing some of this in A-level geography, but it's like this soil mechanics isn't really exactly the same. This is like soil mechanics for engineering. This is soils for engineering. So, uh, right, paragraph 2. The destructive process in the formation of soil from rock may be either physical or chemical. The physical process may be erosion by the action of wind, water, or glaciers, or disintegration caused by alternate freezing and thawing in cracks in the rock. The resultant soil particles retain the same composition as that of the parent rock. Particles of this type are approximately equidimensional and are described as being of bulky form. The particles may be angular, subangular, or rounded. The particles occur in a wide range of sizes, from boulders down to the fine rock flour formed by the grinding actions of glaciers. The structural arrangement of bulky particles, figure 1.1, in the next, that's on the next page. So figure one, here it is. Figure one is here. This is the diagram they're talking about. Go back a second. The structural arrangement of bulky particles, figure 1.1, is described as single grain, each particle being in direct contact with the joining particles without there being any bond or cohesion between them. So I just repeat that. The structural arrangement of bulky particles is described as single grain, each particle being in direct contact with the joining particles without there being any bond or cohesion between them. The structure may be loose, medium dense, or dense, depending on the way in which the particles are packed together. The chemical process results in changes in the material form of the parent rock due to the action of water, especially if it contains traces of acid or alkali, oxygen, and carbon dioxide. Chemical weathering results in the formation of groups of crystalline particles of colloidal size, I hope I've said that right, less than 0.002 millimeters, known as the clay minerals. The clay mineral kaolinite, for example, is formed by the breakdown of feldspar by the action of water and carbon dioxide. Most clay mineral particles are of plate-like form, having a high specific surface, i.e. a high surface area to mass ratio, with the results that their properties are influenced significantly by surface forces. Long needle-shaped particles can also occur but are comparatively rare. The basic structural units of most clay minerals consist of a silica tetrahedron and an alumina octahedron, figure 2.1. So that's there. Oh, right. So silica tetrahedron, aluminium octahedron, tetrahedron, like a triangle one. So silicon in the middle with oxygen around it. Aluminium octahedron, aluminium with hydroxyl around it. Alumina sheet, silica sheet, so it's wide. Clay minerals, basic units. Yes, it's helping me to zoom in on these things, because on the textbook, I've got to admit, I find it hard to read the small writing. This book should be in A4. It's in A5. It's too small for me. I can't read it. That's why I have to zoom in on it. So I was just repeating that The basic structural units of most clay minerals consist of a silica tetrahedron and an alumina octahedron. Silicon and alumina may be partially replaced by other elements in these units, these being those known as isomorphous substitution. The basic units combine to form sheet structures which are represented symbolically in figure 1.2b. The various clay minerals are formed by the stacking of combinations of the basic sheet structures with different forms of bonding being combined sheets. The structures of the principal clay minerals are represented in figure 1.3. So you got A, it's got like a little rectangle with then a little layer stacked up. H bond, H bond, H bond, and then it's got K plus, kaolinite, illite, montmorillonite. I've not really seen them before. I don't know what that H bond means. Oh, H2O water. H bond, H bond, H bond, K plus, K plus. Right. Kaolinite consists of a structure based on a single sheet of silica tetrahedrons combined with a single sheet of aluminum octahedrons. There is very limited isomorphous substitution. The combined silica alumina sheets are held together fairly tightly by hydrogen bonding. A kaolinite particle may consist of over 100 stacks. Illite has a basic structure consisting of a sheet of aluminium octahedrons between it and combined with two sheets of silica tetrahedrons. In the octahedron sheet, there was a partial substitution of aluminium by magnesium and iron, and in the tetrahedral sheet, there was a partial substitution of silicon by aluminium. The combined sheets are linked together by fairly weak bonding due to non-exchangeable potassium ions held between them. Montmorillonite has the same basic structure as illite. In the octahedral sheet, there is partial substitution of aluminium by magnesium. The space between the combined sheets is occupied by water molecules and exchangeable cautions other than potassium. There is a very weak bond between the combined sheets due to these ions. Considerable swelling of montmorillonite can occur due to additional water being absorbed between the combined sheets. The surfaces of clay mineral particles carry residual negative charges. Get that off there. Mainly as a result of the isomorphous substitutions of aluminium or silicon atoms by atoms of lower valency, but also due to dissociation of hydroxyl ions. Unsatisfied charges due to broken bonds at the edges of particles also occur. The negative charge results in cations present in the water in the void space between attached to the particles. The cautions are not held strongly, and if the nature of water changes, can be replaced by other cautions, a phenomenon referred to as caution exchange. The cautions are attracted to a clay mineral particle because of the negative surface charges, but at the same time tend to move away from each other because of their thermal energy. The net effect is that the cautions form a dispersed layer adjacent to the particle, the caution concentration decreasing with increasing distance from the surface until the... Oh my goodness, this is hard. It's hard to understand it, isn't it? It's hard to understand what they're talking about because I don't find this book very good, to be honest. I'm just going to finish this video, then I think I'm going to need to go through this again because it's just, I don't know, but they've done a lot of description about what things, and it's hard to really follow it, and I find the diagrams are really bad. I don't really understand, like, where was I? Oh yeah, where were we? Just repeat the last sentence. The net effect is that the cautions form a dispersed layer adjacent to the particle. The caution concentration decreasing with increasing distance from the surface until the concentration becomes equal to the normal water in the void space. The term double layer describes the negatively charged particle surface and the dispersed layer of cautions. For a given particle, the thickness of the Gaussian layer depends mainly on the valency and concentration of the Gaussians. An increase in valency due to Gaussian exchange or an increase in concentration will result in a decrease in layer thickness. Temperature also affects Gaussian layer thickness. An increase in temperature results in a decrease in layer thickness. Right, next paragraph. Layers of water molecules are held round a clay mineral particle by hydrogen bonding, and because water molecules are dipolar by attraction to the negatively charged surfaces, in addition, the exchangeable Gaussians attract water, they become hydrated. The particle is thus surrounded by a layer of absorbed water. The water nearest the particle is strongly held and appears to have a high viscosity. The viscosity decreases with increasing distance from the particle surface to that of a free water at the boundary of the absorbed layer. Adsorbed water molecules can move relatively freely parallel to the particle surface, but movement perpendicular to the surface is restricted. Forces of repulsion and attraction act between adjacent clay mineral particles. Repulsion occurs between the like charges of the double layers. The force of repulsion depending on the characteristics of the layers. An increase in Gaussian valency or concentration will result in a decrease in repulsive force and vice versa. Attraction between particles is due to the short-range van der Waals forces. These forces are independent of the double layer characteristics and decrease rapidly with increasing distance between particles. The net interparticle forces influence the structural form assumed by the clay mineral particles. If there is net repulsion, the particles tend to assume a face-to-face orientation, this being referred to as a dispersed structure. If, on the other hand, there is a net attraction, the orientation of the particles tends to be edge-to-face or edge-to-edge, this being referred to as a flocculated structure. These structures involving interaction between single clay mineral particles are illustrated in figure 1.4a and b. Oh, right. So figure 1.4a is here. Dispersed. Oh yeah, so you got a few like around there, and then B is flocculated. Don't know what that word means. Just like scattered, I guess, but not in little bundles like C or D. Just single ones spread. Oh. All right. So we've got to go to here. Next page. In natural clays, which normally contain a significant proportion of larger, bulky particles, the structural arrangement can be extremely complex. Interaction between single clay mineral particles is rare, the tendency being for the formation of elementary aggregations of particles, also referred to as domains, with a face-to-face orientation. In turns, these elementary aggregations combine to form larger assemblages, the structure of which is influenced by the depositional environment. Two possible forms of particle assemblage known as the bookhouse and turbostratic structures are illustrated in figure 1.4c and d. So this is like C here, like a cluster of them, and C and D. Assemblages can also occur in the form of connectors or arrangements between large particles. An example of the structure of a natural clay is shown in figure 4.14. Particle sizes and sorts can vary from over 100 millimeters to less than Assemblages can also occur in the form of connectors or a matrix between larger particles. An example of the structure of a natural clay is shown in figure 1.4a. I don't know about you, but I am really struggling to understand what they're talking about here. I don't really understand it, and the diagrams are bad, and the text is just too long. They're talking about things that how are you supposed to know about van der Waals force unless you've done chemistry or physics or something? And it's not referencing. It doesn't say read this first so you can understand it. It's just I find it's just incredibly difficult to understand. I don't know what they're talking about. It's hard to stay interested in it, isn't it? I just find it's also the way it's presented is quite boring. It seems pointless and meaningless as well. So I think we got to come back over this and try and improve. I'm going to try and redo this so I could understand what's happening. it says so particle sizes in soils can vary from over 100 millimeters to less than 0.001 millimeters. In British standards, the size ranges detailed in Figure 1 are specified. In Figure 1.5, the terms clay, silt are used to describe only the sizes of particles between specific limits. However, the same terms are also used to describe particular types of soil. For example, clay is a type of soil possessing cohesion and plasticity, which normally consists of the particles in both the clay size and the silt size ranges. Most types of soil consist of a graded mixture of particles from two or more size ranges. All clay size particles are not necessarily clay mineral particles. The finest rock flour particles may be of a clay size. If clay mineral particles are present, they usually exert considerable influence on the properties of soil, an influence out of all proportion to their percentage by weight in the soil. Soil whose properties are influenced mainly by clay and silt size particles are referred to as fine or fine graded soils. Those whose properties are influenced mainly by sand and gravel size particles are referred to as coarse or coarse grained soils. In more general terms, a soil is considered to be cohesive if the particles adhere after wetting and subsequent drying, and if the subsequent force is then required to crumble the soil. This does not include soils whose particles adhere when wet due to surface tension. A soil which does not possess the characteristic is said to be cohesionless. So that's one. The last paragraph actually I could understand. It says, in more general terms, a soil is considered to be cohesive if the particles adhere after wetting and subsequent drying, and if the significant force is then required to crumble the soil. This does not include soils whose particles adhere when wet due to surface tension. A soil which does not possess these characteristics is said to be cohesionless. And then just go back to it says a particle size analysis. Figure 5.1 particle size ranges. So boulders, I think it doesn't particle size in millimeters. Boulders is 200, cobbles 100, coarse 600, gravel, from 2 to 60 is gravel, from 0.6 to 2 is sand, silt is from 0.002 to 0.06, clay. So that little chart I can understand, because like sand is on the beach, isn't it? Like, you got Bournemouth Beach is sandy and some silty, fine. Gravel is like Brighton Beach with the cobbles and the gravel. Bigger boulders upwards, and then clay is less than 0.002. So I hope you found this video useful. This is obviously, as I just said, I found it really hard to understand it, and it doesn't really. I would just say as well, it doesn't get you into. It doesn't kick off the book very well because it's really hard to understand, and really struggling to understand what they're talking about. And they're referencing loads of different principles without diagrams, and the text is too long and it's hard to find it interesting and to understand it. To understand it, you have to be able to take it in. But what I've done there is I've read it out, but I still don't understand. Hopefully that can change that. Hopefully you found this video useful, and then I can see you in the next video. Thanks for watching. Please like and subscribe, and then if you've got comments too, like, did you find the text, is it hard to read? Did you, like me, do you need the text to be bigger on a bigger sheet? Because this is only on A5, and then how could these guys improve their presentation? Could they use color diagrams instead of these just, and this book, it's just like massive boring chunks of text. The diagrams aren't really very good, because I think if you've got a text and you're talking about a diagram, the diagram should be on the same page so you can easily see it, instead of what they've done. It doesn't make sense. It's not very good, not very well edited, is it? But hopefully we can go through and try and work out some things. Thanks for watching. See you in the next video. Bye.